there are any problems, let me know. So now we go to our second topic, which would be number systems. As you remember, we have talked about, is it working? Okay. We have talked about our switches to systems and told you about that. As you can see, at the highest level we have system, at the lowest level we have transistors. So we are going to start with the basic of all of the computing world, which would be a binary number system. You have already, I guess, know binary, and we are talking about the binary systems. So why do we use binary? I guess you already know, and how to make binary numbers. So binary is the numbers in base 2. So when we are a numbering system, when do we have a numbering system with base n, it means that for counting we have n signs. For example, in decimal, which we are using every day in our world, 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, and so on, we are using 10 digits, 10 signs. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits. And all of the numbers are formed from these digits. So when we are saying that, okay, our base is 2, a numbering system which the base is 2. So it means that how many digits, how many signs do we have? 2. What and what? 0 and 1. 0 and 1. And the computers work with 0 and 1. Do you know why? Anybody, any idea why?
Because it's easy to have a switch that goes on and off.
Yes. Very good. Perfect. Because we are using switches, transistors, as I told you. And through transistor and switches have 2 states, off, on. So one of them would represent 0, the other one would represent 1. So the computers don't understand words. They just use 0 and 1s. So that's why we are going to learn about binary systems that I am sure that you have already know about that. It's not working. Okay. Binary number is base 2. We have 2 digits, 0 and 1. That's it. So how do we use these? You know these things, or have you seen that before? Decimal, binary, in high school? In high school, yeah, I guess you should have seen that, but we have to go through it fast, so I go faster. Decimal numbers is what we use every day. 43. 43 means there is a number which has 2 digits, 4 and 3, and if you look at 43, it is actually like that. 43. Let me see if I could write. Okay, 43. For example, let's say that we have a fraction part also, 43.25. So when we have a number in decimal system, this is like that. So in every base, we have a decimal point, a point, which here is decimal point. In binary would be binary point. In octal, it would be octal point. In hexadecimal, it would be hexa point, so on. So there is a point which separates integer part from the fraction part. At this point, at the left of this point, there are values, there are digits which are valued based on the positive numbers of the power of the base. What do I mean? This is the first digit. So it should be, it has a value of, a weight of 10 to the 0. The next one has a weight of 10 to the 1. The next one would 10 to the 2. The last one 10 to the 3, 10 to the 4, 10 to the 5, 10 to the 6, and so on. So these are weighted. This is something that you know every day. I am saying something that it makes it more complicated. We are knowing these things from the preschool. And at that part, they are weighted at negative powers of 10. So the first one should be weighted by 10 to the minus 1. The next one 10 to the minus 2, and so on. So this number 43.25, what does it mean? It means 3 times 10 to the 0, which is 1. So I will put 1. 3 times 1 plus 4 times 10 to the 1, which is 10. 4 times 10, which is 40. 40 plus 3. And at the fraction part, it is 2 times 10 to the minus 1, which is 0.1. And 5 times 10 to the minus 2, which is 0.5 times 0. So this is the number. 4 times 10 is 40, plus 3, 43, plus 2 times 0.1, which is 0.2, plus 5 times 0.01, which is 0.05. Then the total would be 43.25. This is the decimal number. I write it here so you got the idea of the base system, and then we go to the binary, and it's exactly the same thing in the binary. So let me erase this. For example, 25.13. 25.13 is 5 to the times 10 to the 0, 2 to the times to the 1, 2 by 10, 5 by 1, and 1 to 10 to the minus 1, and 3 to the times 10 to the minus 2. If you calculate this, it would be 25.13. And this is the integer part, and that is the fraction part. But exactly the same we are going to in the binary. Binary, the base is 2. So if the base is 2, it means that this is the binary point. Any digit at the left of the point is weighted with positive powers of 2. And any digit at the right of the point will be weighted by negative powers of 2. So, for example, let's say this is the number that we are going to see the equivalent value in decimal system. In decimal, we are converting binary to decimal now. The binary number is this is 1101.0010. This is the binary number that we are going to convert to decimal. Okay. So as you could see, the first digit in the left of the point is weighted by 2 to the 0. The next one will be weighted by 2 to the 1, and then 2 to the 2, 2 to the 3, and 2 to the 4. And at the right side, 2 to the minus 1, 2 to the minus 2, and so on. So what will be the result? Okay. 1, this one. This one times to the 0. 0 to the times to the 2 to the 1. 0 again. Then 1, 2 to the 3, and this one 2 to the 4. Plus 0, 2 to the minus 1. 0, 2 to the minus 2. 0 times anything would be 0. So they are not calculated in our sum. 1, 2 to the minus 3. 2 to the minus 3 is 2. 2 to the minus 3 is 1. 2, 2, 3 is 1 over 8, which is, 1, 2, 5. This is 1 over 8. 1 to 5. Okay? So if you add these things together, 1 times 2 to the 4 is 16. 16 plus 1 to the 3 is 8. 16 plus 8 is 24. This is 0, this is 0, this is 1. 24 plus 1 is 25. So the integer part would be 25. And the fraction part 0, 0, and this is 0.125. So it is 125. So 25.125. This is the equivalent decimal of that binary number. The binary number that is there, the equivalent decimal is. So when I ask you, you convert binary to decimal, you do this. You find the binary point. At the left, you times to the positive power of 2. At the right, you times to the power negative power of 2, and then you sum up. So this is again integer part, and this is fraction part. Now, how do we convert decimal to binary? Now, we have a number 29.61. What would be the binary equivalent of that? It is maybe a little more difficult, because we are thinking very good in decimal. We could find the decimal equivalent of binary very easily just by doing some kind of multiplication and addition. But this time it is somehow harder. The first method that I tell you, it works better for integer part. Actually, it works for fraction part, but I am using it for integer part. For example, if you see, let me write a number and you tell me, this number, 17. What was the binary equivalent? Anybody idea? Any idea? 17. 17 is 16 plus 1. And 16 is 2 to the 4. So if we start from here, this is 1, this is 2, 3, 4, 5. Oh, sorry. It is 0, the power of 0, 1, 2, 3, 4, and so on. So 16 is 2 to the power. So we have a 16, and then we have a 1, 16 plus 1. So we have 1 here, and we don't have anything else. 16 plus 1 is 17. So the other one is 0, 0, 0. So the binary equivalent of 17 would be 1, 0, 0, 1. Okay? Yeah? For example, 258. What would be the equivalent, the binary equivalent of that? 258. What do you, when seeing that, which power of 2 you recall from that? 256, yeah, exactly. 256. You should, in this case, you should know the power of 2 numbers. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, and so on. Okay, so you should somehow know these numbers. These are the binary numbers. And then you could find out this is 256, so it is 258. It is 256 plus 2. 256 is 2 to the 8. So we have 1 at the 8th position. And then 7, 6, 5, 4, 3, 2, True, 1, and 2. We have 2. So we have 2 to the 1. So this is 1 and this is 0. So this is the equivalent of 258. 1000010. This is the equivalent. So I call this method successive subtraction. Let me show you. It works for a fraction part, but it's harder. I will give you another method for fraction part. So 29.61, what would be the equivalent of binary? So 29. 29 is the integer part. We use successive extraction. The first binary number that you could see which is less than 29 is what? Is 29, the binary numbers. 1, 2, 4, 8, 16, 32, 64. Which one is the closest one to this, 29? 16, exactly. So this is the 16. You should always remember these numbers. So it is 16. So first, you have 29, and you know 16 is there. So you subtract it, you have 13. So which binary number is in 13? The first one is 8. So 13 minus 8 is 5. For 5, we have 4 inside. 5 minus 4 is 1. In 1, we have 1 only. So we don't have 2 here. And so we have 1. So if you look at them, you have 16, 8, 4, and 1. And so you put 1 in these positions, and then the other one would be 0. So we have 1 here, 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 and the rest 0, which would be 0, 0, 0, 1, 1, 1, 0, 1. This is the binary number of 29. So this is successive subtraction. You could do it in mind without writing. When you see, for example, number, let's say, 67. 67 is 64 plus 2 plus 1. So we have 3 bits there. The other one are 0. So you have to know where is 64, where is 2, where is 1, and then you write. It needs practice. But the other very systematic way is successive division. If you divide the number by 2, the integer part. For the fraction part, we will talk later. For the integer part, if you divide it by 2, then you keep the remainders and go up. Let's do it. Let's do 29. So we start by 29. 29 divided by 2. It will be 14, and the remainder would be 1. 14 times 2 is 28, and the remainder would be 1. So please remember this 1. Okay. And then 14, we have 14 here. So now we divide 14 by 2. 14 divided by 2. The result would be 7, and the remainder would be 0. Okay, now what do we have? We have 7 now. So now we go for 7. 7 divide by 2. So 7 by 2 is 3. The result is 3. And the remainder is 1. So remember this 1. Now we have 3. 3 divided by 2. The result would be 1. 1 times 2 is 2. And the remainder would be 1. Now what do we have? We have 1. Either you could stop here and then consider that, or you could do 1 also. 1 divided by 2, the result would be 0, and the remainder would be 1. So either you consider this 1 as the last digit, or you continue dividing and consider this 1 as the last digit. They are the same. So what would be the binary value? The binary value, you should start from the first one and go one by one. 1 is this. 0, 1, 1, 1. So the binary number would be 1, 1, 1, 0, 1. 1, 1, 1, 0, 1 for the integer part, which is 29. So what to do with the fraction part, 0.61? How do we calculate the binary equivalent of that? 0.61. In the fraction part, what do we do? In the integer part, we divide it by 2. In fraction, what do we do? What do you guess? What is your guess? Multiply by 2. Yeah? Okay, that's what we do. So 0.61 was the fraction part. So we start multiplying by 2. 61 times 2 is 1.22. Okay, so remember this one. Then, what do we have here? 0.22. 0.22 times 2, which is 0.44. So remember this 0. Then we have 0.44 times 2, which is 88. 0.88. Then we have 0.88 times 2, which is 1.96. So we have 1.96. Now we have 96 times 2, which is 1.92. You could continue because this is a fraction, and the fraction could continue unlimitedly. So you could continue. It has fraction part of binary up to whatever it goes. It might not end, it might end. For example, if the fraction part of decimal was 25, it was ending after 2 multiplication. Because we will reach a point which the multiplication is 1.0, so we get 1, and then this is 0, so when you multiply by 2, it is 0, 0, 0, 0. But here it will continue. So 92, again, you could do it 90.92 by 2, 1.84. Again, 84 times 2, and so on. So what is the time? I don't have the time. What time is it now? 50. Oh, so we have to finish. Okay. So this is the last slide. So what would be the equivalent? The equivalent would be this. 0.61 in decimal equals to 1. 1. This is 1. 1, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, and it continues. We just put this number. We can continue more to have more fraction parts. So this is how to change the binary to decimal. So the whole thing would be something like that. The fraction part, the integer part. The integer part, 29. This 0.6 part is this one. Okay. So we are at the slide number 9. We will continue from slide number 10 in the next session, which would be on Tuesday. Yeah?
Are you going to upload these slides?
Yes, yes.
And are we going to start the flip classroom model next week?
From this one, huh?
Right. But are we going to start the flip classroom?
From class?
Yeah, from next week. We have to be doing the flip classroom.
Flip classroom. Oh, I wanted to go through your reflection on Flip. It was very interesting. I read, I guess, 32 of you have put your feedback in Flip mode. Out of 32, 29 told us it's good to try it, and 3 said they are not sure, and maybe they prefer not traditional way. So I am going to try. Maybe not next week. Give me a time to prepare the material. So Monday, we will see each other in Monday, either flipped or in person. Okay. Yes?
Are we going to have a tutorial today then with RTA?
No, not today. Because I have to reach a point that I give you problems to think about it, and then and the lab also, I told you that it might be next week, but it depends on how we reach to the, because you need to do some lab, yeah. Maybe next week, maybe the next after the next week. Okay.
So will it be posted when there's
Yes,
still active
exactly,
tutorial?
exactly.
So we'll be aware of it.
Yes,
Okay,
yes.
because I had a medical appointment last class, so I wasn't here.
Oh, okay,
So I was just going through the syllabus, and
okay,
so I was just looking at the scheme here.
okay.
The reflections. So how does that work? Do we have to fill out the?
After each content, there is a reflection. You see? Let me show you. Let me stop this.